Good morning. We're getting started officially, and there are just 3 of us in the class right now besides me. 2 will be here and 1 who's got a work conflict and will always be attending at a distance, watching the videos later. We'll talk about how exams are going to work when that time comes. It's only for the 1 exam, so I'm not really too worried. We'll figure something out. Some of you don't have the book yet, so this morning I pushed into Slack the PDF that I made of cutting and pasting from the book. So you just click on it, you can pull it down. If you've never used Slack before, it's very much like Teams. Actually, historically, Slack is much, much earlier than Teams. Microsoft came racing, as far as I understand, racing to the forefront with their product, trying to outdo somebody else. But Slack is pretty laid back, is what I think. It's easy to work with. We can direct message, as Fatma, you have to me, and you can work on the channel, which is shareable by everybody. So anything you put on the channel, just understand everybody can see it. As a matter of fact, I've only got 1 private channel on here, and that's for my hearing aid project. I don't really feel worried about that because people from the other classes have no reason to look at it, but it's available. So what I will do, though, since I'm getting into that for a moment, if you start direct messaging me, and you have a question about a question, or you want to raise an issue, and then I say, hey, this is pretty interesting, as I write back to you, I may decide I'm also going to move it onto the channel for the class, so that way other people can see it. And if you don't feel like you want to do that from the get-go, that's fine, but the purpose of the channel is to have some common dialogue. We all can talk on it. You can do mentions with the ampersand, so you can go at somebody's name and then that will pop up and then they'll make sure to get an alert from you too. I'm always a little bit confused about how I get alerted from Slack. You use it at Keysight though, right?
Yeah, its notification is very confusing. I know Kevin about it.
Yeah. But when you open up Slack again on your phone or whatever, you will see in bold this channel.
Mm-hmm.
So that will work for the channel. For an individual direct message, that always alerts me on my phone or on my app. If you're using the web version, I don't know, because I don't use the web version. I mean, I just have the app installed and it works best. So you can start saying you're getting slacked, which is what I say when I feel like I'm getting overwhelmed. I'm by no means overwhelmed, but I did do this before, and it worked well. So, I mean, I will be there as much as I can, and I was having people Slack messaging me all over the weekend. They were joining, and then spontaneously in my other class, they just started talking to me like, what do you think about this? Nothing to do with the class, just something else. So sometimes people want to just ask questions, so that's fine. And because I'm using the free version, somebody also asked me, does it cost any money? No, it doesn't cost any money, but my understanding when I first got involved with it was that because I have the free version, I don't have as much depth in terms of message history. So eventually it will roll off, but it rolls off from the oldest message forward. And I don't know if I've even lost any messages since I started using it. So what else is there? I haven't really gotten Zoom working the way I'd like it to work for me, but you can see that I do have the Zoom app installed. There's quite a number of apps you can put in, but in the free version you can only put a couple of apps in for free. So I have Zoom in, and then I had Daily, which is another type of video conferencing. It's a free video conference. They all work though similarly. You just type your message and put a slash in here, and then if I was going to do Daily, I think this is what it's going to do. Daily, we'll start a meeting note, and then as soon as I hit enter, it's going to come up with a link, and then we can all click on the link, and then it'll bring it up in the web browser, and then we can start video
I'm gonna say, I don't know if you know, but in Slack, you can add hot links on top of each channel. So you could like link the website and so on.
chatting. Okay. Maybe I did or didn't know that, but yeah, any ideas you want to share, because you use it a lot more than I do, that'd be fine. I know sometimes you can do direct messaging in a trio, right?
Mm-hmm.
I did that numerous times. This link is here. It's going to not mean anything because I'm never going to use it, but I just thought I'd point that out. You can actually go to the internet and find out all the tips, and I've done that, but I haven't practiced at all. I practice doing engineering rather than this, but sometimes you got to spend just a few moments learning how to use something.
Mm-hmm.
Okay, so back over to where we were. I really didn't get a chance to finish this, and I'm not going to do everything that's in here, but I just want to talk a little bit about propagation modeling and then the other introductory type stuff. So in what we're dealing with in this class, we can consider communications mediums of all different types. It's not restricted to just line of sight. Free-space propagation, it can be guided through coaxial cable, twisted pair, optical fiber, acoustical, everything and anything. So this is just a picture that comes from the book, though. It just shows you that, okay, in terms of electromagnetic wave propagation, we have, if we're doing satellite communications, which is like, say, geostationary or something of that sort, which is very common, right? We do a lot of comms, geostationary for television, military government operations, cloud, this and that. So we have trans-ionospheric communications, which means that the ionosphere is ionized layer that sits in the outer atmosphere, and what does it do? It has ions in it, and what do ions do? They look like a mesh of metal-like particles or charged particles. So think of your microwave oven. It has a screen on its door, right? It has little holes in it. What does it do? It doesn't let the microwave frequencies through, or at least we presume that it doesn't, right? Because if you're watching something cook, you stare at it and say, I think it's done or it's about ready to cook over. So it acts like a filter. So what's happening here is that if you're at a low enough frequency, though, it looks just like it'll reflect at lower frequencies, and then higher frequencies it will pass through, and that's how we get our like 12 gigahertz is a popular frequency band for geostationary, and then lower frequencies like DHF and UHF will not penetrate through, and the ionosphere also raises and lowers depending upon what the sunlight is doing. So in the evening it comes down lower. You have to I always have to think of geometry, but the thing is only this tall and it bounces off. Then this angle, I'm using my hands to say this is transmitter, reflects off, angle of incidence, angle of reflection, right, from geometry. It can cover a greater distance. That ionosphere is up higher, then that angle of incidence and reflection is going to be sharper, and the distance that will bounce will be less. Why does that matter? Well, we rely on that fact a lot in traditional broadcasting from the beginning of broadcasting history, like around 1900 and so on, where we had skip wave propagation by reflecting off the ionosphere, and AM broadcasting, which is only at around 1.5 megahertz for the carrier frequency makes use of that a lot. So I can listen to, since you're from New York City, you can listen to some station in New York City in the evening on an AM receiver. And then the other stations have to shut off because everybody can hear everybody else if they're reusing the frequencies, which is another fundamental concept that propagation is used to our advantage and disadvantage, is that if it's a locale, we can reuse frequencies safely. Like the Denver market can reuse its FM broadcasting and AM broadcasting fairly well by both power control and relying on the ionosphere. And then in the evening, when the ionosphere comes down, the selected AM stations are only allowed to stay at full power because otherwise they would interfere with one another. And that's, was it KOA, I think, up in Denver is one of those stations.
Sorry.
Yeah.
So you're saying in the daytime more stations can run, and then at night there's less that are allowed to run
For AM broadcasts.
because they can project further?
Yeah, because of that change in the ionosphere. It takes more power though, too. I mean, we have
Right.
1 over R squared is the rate at which the power attenuates for free space propagation, and that's stuff you learn in EM fields, but also just think about what happens if you've got a point source, just a point that can radiate. I always think of it as its wave radiates off, it becomes a plane wave not too far off from the source, and that plane wave is radiating in equal directions if it's a true point source, and then it's painting its power in watts as power in watts per meter squared, and as the sphere gets bigger and bigger and bigger, then the density or power density is less and less and less. And that same idea works for the receiver, because we have reciprocity in electromagnetics, which says whatever the pattern is that you're radiating with, if you're receiving with an omni or with a directionalized antenna, you capture a piece of that space or area, right? So if the effective area of your antenna is 1 meter squared, then you capture 1 meter squared of RF power, and if it was at a, as the distance grows, then that flux density is less. You still capture a meter squared worth, but it's a lot less in flux density, and then that becomes your received power in, usually in dBm or something like that, decibels relative to 1 milliwatt of power. All makes sense, right? It's very fundamental, but it's stuff that I think no matter where you're at, sometimes you have to just sort of shake your head and say, not saying no, but just like jolt yourself a little bit and say, yeah, there's still these foundations to everything that goes on in communications theory, and that's one of them. So you also have pure line of sight, which would be direct line of sight, say, to an aircraft or up trans-ionosphere, up into space, that they're not perturbed by too much. There is things in the atmosphere. When we're doing ground wave, though, and this picture here just shows antenna to antenna, like it might be my cell phone up to the towers that are behind the campus, right? Then it's not so simple, and I'll look at a little example of multipath and that stuff here in a few moments, but we do have a line of sight. If we have a line of sight, we call that the direct path, and then we have the diffuse paths, and I'll show you a picture of that. That is a huge thing in every form of wireless that we do, whether it be cellular, Wi-Fi, Bluetooth, I guess, my watch talking to my cell phone, and so on and so forth. This just comes from the book again. These are just the classifications of the frequency bands. One of the things that I find amusing is this letter designation chart, which he has in the book. The old listing are the letters you see in blue. So C-band or L-band, let's just take L-band. What frequency is GPS on? Does everybody have that burned in their brain? I mean, I've done GPS work, so there's several carrier frequencies, but 1.575 gigahertz is L1 GPS, and that's the dominant carrier that we would use on our cell phone. There's an L2, I think an L3. They're all close by, but so it's in the L band. But there was an attempt made to reorganize the bands into a different lettering system. I still don't hear anybody talk about the D band or the other, that green column. Has anybody bumped into that? What is it? What's up with that? I mean, you're from Iran, so you're probably all metric in your country. Or maybe not. Are there other units of measures that your society would use other than metric units?
No, I'm not sure.
Okay, you're not sure. Well, the United States, we're a boiling or melting pot nation from all different countries that had people immigrate here. So we descended from Great Britain a lot originally, and then other Western European countries dominated. I mean, that's where my ancestors came from. Germany and Norway is my background, but we attempted when I was in school, elementary school, that we were going to become a country using the metric system and give up using inches and feet in mils, instead use millimeters and micrometers and so on. It never worked. It's used in some things, but I think this band designation is kind of a similar example. So we have C-band, X-band, KU, and KA. 5G is way up here and higher, whereas 4G and below stayed with the original frequency bands that were allocated to them. I have a little note on that here too, historically. So 5G is a huge departure in terms of frequency bands, but not entirely, because as I said right in here, see if my pen is working again. I'll just make sure it's working. Electromagnetic spectrum is a natural resource. We only have so much of it. We only have so much water, and so on and so forth. So we have to treat it that way, and it's highly regulated at the country level and at the world level. So at the country level, we have the Federal Communications Commission. At the world level, we have the International Telecommunications Union, and then they have conferences, but so ITU are rules that govern the world, and of course, all the rules that are set up are only during non-wartime. So if there's a conflict going on, forget about the rules. People will do what they have to do. Not that it's right, but it's just the way it works out. You can't infer that to say, I'm going to go through a red light because I'm in an emergency, but people do that, right? What's a good example? I mean, trying to think. I do see people occasionally do things like that, and I'm like, wow, I'm glad I wasn't there, but usually they'll stop. They might be taking their wife to the hospital because a baby's going to be delivered, and et cetera, et cetera. But so within the FCC, we also have the National Telecommunications and Information Administration, or NTIA. They actually have a lab up in Boulder, Colorado, which I've been up there at least once. They make a lot of recommendations and publish things. They do experiments. They have standard hardware configurations and other things that are used for establishing standards related to telecommunications. This chart also appears in the book. It just lays out some of the other things that have gone on traditionally. And I'm only going to stop here for a second and say that traditionally, as cellular came into being, it originally had, in the first generation of cellular, it was around 900 megahertz, just under 900. So that's still part of the cellular band that's used right now for 4G. And then they came along with petitioning the FCC to get another band that was called the PCS band, Personal Communication Services. And that started out being dominated by code division multiple access in 3G. I think 2G too, I'm trying to remember. It's fuzzing out in my brain which happened when. But those are pretty much intimately linked together still in 4G. I mean, your service provider has, depending upon who it is, for me it's AT&T, if yours is Verizon, they will own certain bands, either in those two frequency centers for, say, the Colorado Springs market, and then Denver will have something different. Traditionally, though, it depends upon how the network grew and so on and so forth, who owns what bands and who merged with who, because Sprint and my brain's going to draw a blank. Sprint merged with, what's the company? Can you, either of you think of that? Since you're not from the United States, I wouldn't expect you to know, but
I don't remember.
I can't think of it right now. And I used to work in this a lot myself. I used to know this stuff because I worked for a company that did a lot of field measurements, and they were out working for one company or another, doing site studies, looking at interference issues and so on. You can see GPS is in there. ISM band, though, industrial, scientific, and medical, is covering many bands, and you can see the groupings of the bands in there. So I don't think they're all in here. That particular ISM band is where the Wi-Fi band is found.
Mm-hmm.
Bluetooth is in there. A lot of stuff is thrown in there. It's very congested. As I found out in my Wednesday class, I ended up getting a new mouse, and it's a mouse that has both Bluetooth, and it's a Logitech mouse. It's a universal mouse. It has 3 channels of RF or coding you can establish. So I can just flip a little button on the back, and I can decide what device do I want to access on my desktop without changing any cables or anything. Kind of cool. But I found out I'm using the dongle or the RF nub. I found out on Wednesday it started acting up, and I'm not using the Bluetooth because this tablet, although it has it won't let me pair my mouse with the laptop on Windows 10. But then I found out in the middle of class that it just started acting very squirrely, and I went back to my office and it worked just fine, so I'm concluding that there's some interference going on between the bands. I mean, I know that Bluetooth and Wi-Fi have to coexist. So Bluetooth plays back and hops around, whereas Wi-Fi stays on a designated channel unless your router is forced to move somewhere. So it was a little bit frustrating. I decided I'd bring it to this classroom and see if I have an issue with it. Why do I say all these things? Because once you start studying more and more about communication systems and communications theory, you start wanting to utilize some of that knowledge in your own personal life, like why am I having a problem? What's happening? That sort of thing. Another thing in propagation I didn't mention that's mentioned in the book is oxygen and water vapor absorption. So this is a very interesting thing to be aware of for satellite communications. water molecules and oxygen molecules have resonances based on the sizes of those molecules. So an RF hits it, it can act like a resonator, and it'll act like a notch filter then. So you can see the solid line is oxygen, and at 23, 62, and 120, those are, well, 62 and 120 is where there's a resonance for the oxygen. Those are like harmonics. I don't know why they're not exact, but it must have something to do with not being linear. You know, generally think in microwave circuits we have harmonic relationship, but at any rate, 62 gigahertz would have a hard time propagating through the atmosphere and getting up to a satellite. Now, can you think how that can be an advantage? Why or how would we utilize that in a constructive way?
We'd use those for more short-range communication, knowing that they wouldn't interfere with other channels as easily.
Okay, where particularly on the ground or up in space?
I guess you could use it in space to talk between
Crosslinks. Yeah, crosslink. So a crosslink in space, that frequency band would be somewhat secure from being eavesdropped by a station on the ground. Now, another satellite up there could eavesdrop if the beam spread was wide enough, but yeah, so exactly, multiple or reuse of resources based on just a physical property, and water vapor has the resonance is shown there too. We also have to contend with rainfall rate, and that's a statistical property because it's not always raining out, but when you have rainfall rates in terms of millimeters per hour, then we get different attenuation rates, and in general you can see it's going up with the carrier frequency. So if you were like in 5G, which is going to be way up there, 30 gigahertz and so on, it's going to have a lot more attenuation than you would at lower frequency. So more attenuation, you can see the axis there is dB per kilometer. Okay, a lot more could be said about that too, but I'm trying to think. The statistics are, when is a rainfall rate, when is a large thunderstorm going to come through, and when isn't it? So people keep statistics, and if you're planning a link budget of any type, whether it be just on the ground or going up into space, you can count on a large rainfall rate occurring statistically so many times per year, more often certain times of the year. So links are supposed to be designed, like let's just suppose, well, here's a scenario where you can't really fix it. Suppose your cable TV provider is downlinking a satellite from the network. It's maybe coming out of New York City or something like that where it's uplinked. New York City, the uplinking is fine. Downlinking in Colorado Springs or some part of the country that's getting an extremely high rainfall rate, what are we going to do? We're going to design the link to handle a certain amount of rainfall rate to have what's called the link margin, but if it's an extremely high rainfall rate, we'll just take an outage. We just won't have it work. I have a brother that lives in Louisiana, Baton Rouge, and what he was doing all weekend was preparing for the hurricane that came through yesterday. He had his generator. He said he ran his Wi-Fi hop off his generator and was able to get Wi-Fi out to his devices in his house. And I guess because the power was out, that the network, the cable network that he uses, still stayed alive. But then he said when he wanted to send messages to us siblings that the wireless cell towers was not working really well for him. It took him like 6 tries. Why was he talking to us? I don't know. I mean, it was late for me, but they're an hour earlier there. he wasn't planning on sleeping. He had a large tree from his neighbor fall over his fence, missed taking his fence down, but also missed landing on his car. So I'm sure he'll talk to us more, but I guess in a time of need, I wouldn't be on explaining everything to everybody. I want to know that he's doing well, but I don't need to have him constantly send messages. He was bored though, because I said, aren't you going to try to get some sleep? But I suppose you won't, because he was hearing stuff land on his roof like branches and things. So he said, no, I can't sleep. But we have similar things here, so. So now I'm going to talk a little bit about the mobile radio channel, since it's such a big deal for cellular. It's associated with free space, but there's multipath. And then there's motion involved. So purely free space works well for satellite. There might be some disruptions. I mean, one simple disruption in a satellite link might be trees or other structures like branches are going to move around, so it's going to cause some fading to a certain degree on a satellite channel. But when we're talking about near the surface of the Earth, we've got a lot of obstructions. We have reflectors, diffractors, and refractors that create multipath. So simple picture here is it can become really complex. I know Dr. Semiari likes to do ray tracing. Has he introduced you to ray tracing? Ray tracing? I know he has tools for it because he told me that he bought them. I was interested years ago in ray tracing. I had a PhD student work on ray tracing, modeling for adaptive data rate schemes. And that's an interesting topic unto itself. It's very challenging though. The idea with adaptive data rate is if the link is good right now, you're going to upshift like into your highest gear and run at your highest data rate. If the channel rate deteriorates, then you'll downshift. I'm thinking of a manual transmission where you're going to downshift your car. You're going to send out a much lower data rate or a much simpler modulation scheme. What we were trying to do with the adaptive data rate was predict when it's starting to go into a fade, and I'm going to show you a fading picture here in a moment. So you could already get it downshifted and renegotiate and then gradually upshift. And the guy that I was working with was very interested in, he did an analysis based on information theory, like how to maintain the maximum information flow in the channel when the fading is taking place. So the prediction problem was really hard, and I needed to have a foundation to study that. So we did ray tracing, which is just tracing geometrically, using geometrical optics, how a plane wave would propagate from the transmitter over to the receiver. And you can see the simple picture I have here is there's two rays that lead the transmitter, and you can get a secondary path in the upper reflection off a building and then the lower path. But then you also have, say, the receiver is in motion, like it's driving or walking or something of that sort. So then you also have a changing scenario, and that's what I was interested in because I was considering a car driving and all the multipath and then the changes as a result of the motion. And most students know if they're holding their cell phone, you look at the number of bars, you take a couple of steps one way or another. Have you all observed that the number of bars can change just by taking a couple of steps? So it's fairly changeable. So you can come up with fading channel models and simulators. I did that stuff a long time ago and read papers, attended sessions at conferences, and people have statistical models, and then they have the ray tracing model, which is, like I said, the geometrical optics kind of idea. But the statistical model is what this picture right here shows, and then you can have different amounts of Doppler spreading and delay spreading, and I'll explain that in a second. I'd like to spend more time on that later if we can get the opportunity, but Doppler spreading is due to the motion, and delay spread is due to the richness or lack of richness in the multipath. You know, how many paths are going to arrive, and I'm going to show a picture of that in a second too. And then how are the times of arrival spread? So that controls the delay spread. We'll be looking at the impact of delay spread in simple models just when we study the digital modulation. How are we robust to it, and how does it modify things? The delay spread is or Doppler spread is a little bit more hard to understand, but everybody knows about Doppler from physics. So Doppler spreading is like a modulation applied, a low frequency modulation applied to the waveform as it propagates through space. It turns out in my Python toolkit, I have this time varying delay element where you can introduce both delay spread and Doppler spread, and so you can model that on the computer and just mess things up to see how to mitigate it. You got a question?
I'm gonna say delay spread would probably look something like comb filtering, right?
Yeah, because of the fact that going back to digital signal processing and the idea of the comb filter, where you've got various tabs on the signal as it goes from transmit to receive, you get nulls, particularly if the signal powers are the same on one path as another. Mm-hmm. And that's what this plot here is showing you. This is just showing you versus time how the received signal power can fluctuate. And this was just done with a model, so the minus 80 dBm is just, you know, approximately some sort of channel model scenario where the signal is fluctuating around. So you look at that and you say it's got some very deep fades. I'm seeing about 30 dB depth of fades, you know, minus 80 down to minus 110. Very significant, but they don't happen that often. So then you have the moments of this fade pattern, moments being mean and variance and things of that sort. And then what is the duration of a fade and things like that. And then this pattern intensifies when you drive faster. It occurs more often. Mm-hmm. So the way I like to think about fading, though, and even in a static environment, just like this room, if we were to walk around in the room and be able to measure the power level, it's kind of like an egg crate. Can you visualize? You buy a box of eggs at the store and it's got the place for the eggs to sit, but that egg crate has got the bubbles in it where you're going up and down. So as you're driving across the egg crate, you're going to get this sort of a pattern. Egg crate's an oversimplified view of it, but it's a terrain. It's a terrain-like model. It's not geography, height and depth. It's just signal strength, high and low, and it's in function of 3D space. Do you like that, or does that just sound, I don't need that? It's really, really important, but if we stand still, it's fine, but we don't stand still, so that's the problem. And at microwave frequencies, it doesn't take very much motion to make a secondary path. The phase at that carrier frequency rotates very quickly with just a small, amount of motion because it's such a high frequency.
Right.
I know Keysight has all kinds of neat application notes on all this stuff because I've read some of those and seen them, and there's a lot of good stuff out there. We also have guided wave propagation. I won't say too much about that. Magnetic recording was a big thing at one time. Its magnetic channel is still used to this day, but not like it was, because now we have the solid state drives on our computers. My first PhD student ended up for a time working for a company that made disk drives, and he was very much involved with the magnetic recording channel. which is communications theory just the same. You read and write to the disk. And then optical. Optical has kind of faded away because we have cloud and we don't go anywhere usually to rent a DVD or a Blu-ray too often. You just stream it from the cloud, but for a time these things were really important. But if you're looking at the backbone for the country and the world, fiber optic is king for broadband distribution of data. That's communications theory. It's just done with photons and photon counting and that sort of stuff. And then the project in the Navy I was going to work on with a company here in town until they decided not to fund any proposals was free space optical. I think I mentioned that last week. It was underwater communications between probably a submarine or a boat. I think it was a submarine and then some sort of craft that was going to go out and gather some data and then need to transmit it back to the home base easily, and they were going to do it using free space underwater optical. At a very high data rate, of course. That was the big thing. They were going to do it, I don't know, multiple gigabits per second, so all the data could get streamed back very rapidly. Okay, this is an overview of digital comm, which is the focus of this class. I'm going to let you read about this, but this was a book. This was taken from a book that I had in my office I got in 2010. It's now, dated, but he had a lot of topics that he talked about that just provides a good background on what are some of the factors in digital communications. So the list is pretty long. Then there's the whole focus of digital signal processing, which remember was chapter 1, but I've decided to not focus on that because there's just too many other things to do. So this is a little overview of software-defined radio and its architectures. Then there's a long section in here on the cellular communications roadmap over the years. And this book also had some neat charts in it, so this is one I'll just focus on for a second. This shows you the history of cellular starting in 1980 with the 1G standard. Then we had the 2G standard, 2.5G, 3G, 3.5G. This book also talked about 3.9G, and then it stopped at 5G. And I just added last week, 5G is still rolling out, but we're in an interim right now. There's not just 4G stopped, there's 5G. My phone lights up 5GE or something like that. It's not. AT&T network in Colorado Springs doesn't actually have, I don't think, any 5G sites in town. If they do, I haven't found them yet. My brother-in-law uses Verizon, and he gets them. There's also ultra-wideband that's part of the 5G standard, so he was telling me just yesterday that if he's by some store up on North Academy, he can download all kinds of iTunes music or songs, just bam, because the ultra-wideband part of 5G gives you very high throughput rates. So some discussion of all that stuff in here. If you're at all interested, and I'm just doing other things myself, but I just typed into Google 5G overview, and Qualcomm is a good link to look at because Qualcomm builds chipsets that are used in cell phones in particular. Qualcomm was also the company that started Code Division Multiple Access back in was. Let's just look back here to make sure I know. CDMA showed up in 3G actually. So Qualcomm was big behind CDMA. They pushed that all by themselves. And it's because their foundation was government communications, military use of spread spectrum. Then they remolded it and said, we can use this for multiple access. And they're a very powerful, deep-pocketed company. We'll talk about spread spectrum, but right now that's kind of not in the cellular standards right now, but it was for a time. But another one that I looked at, Thales Group. This one had some pictures that I thought were kind of interesting. This is really huge, so. This is a nice chart just telling you some things about what are the features of 5G. So 8 requirements is what they talk about here. One that I think, this one is more dramatic, is just showing you that 10 gigabits per second is supposedly what you can get, and that's part of that ultra-wideband standard that's available for integrated into 5G. I'm not really super up on all the 5G stuff because I just haven't been doing commercial cellular for quite a while. But I did work in ultra-wideband for a little while, and ultra-wideband is a very interesting scheme also. It was actually going to show up in our wireless routers for a time, over 10 years ago. It was all poised to do that, and then it kind of shifted back and it disappeared for a while. I thought it was like here today, gone tomorrow. Just say a little bit about that. In your lifetimes, you're going to see that. It's just inevitable. Things will get proposed. Things will go away. They won't work out. If you're in research and development, you'll get excited. You'll work with something, and you might leave it, and it might never bear fruit for your company, but it was part of the needs to go run this down to see if it's going to work out. So this is another good site. So I'll just say go look if you're interested. Just do like I did, type 5G overview. Right, that's what I did. Okay. Last thing I want to do on this stuff, and there's details here on how Wi-Fi has changed over the years too. Everything keeps rolling along. I think I've got something else in here that's going to seem like totally an antique. Maybe it doesn't show up until much later. Anybody remember pagers?
Like dial-up?
Just a pager was a little tiny box that a person would wear on their belt, like a doctor would wear them. Do you think pagers still exist to this day? I'm just curious. I'm sure you had them in your country too.
Yeah, I just saw
You-
the movie.
Okay, you saw them in a movie. They're still used. The standard is not gone. It's still out there, and I got involved with it not because I wanted to wear a pager, but when I was working for this company, we were looking at interference potentialities, and pagers are very nasty in the sense that they pulse out digital communications data to all these subscribers, with their encoded with their message tag. But when they do it, it's just a huge amount of power. It's just very powerful. So the pager can be worn. There's not a need for a special antenna. So if you co-locate a pager transmitter with, say, a cellular transmitter, and that was the scenario I saw. I was on the rooftop of a building inside where the equipment was. There was a pager transmitter there, and then there was a CDMA system that we were taking measurements on, and the pager just comes up every so often, and when it came up on the spectrum analyzer, it was just like massive overload because the RF power was just so huge when the pager was bursting out a stream of messages. Here's my discussion about it. So that's another thing that you just can't predict. I mean, what you're involved with, and some types of employers, you'll see old standards and you're just having to cope with legacy equipment, and that's part of being an engineer. You just can't always go down the path of the new stuff and ignore the old legacy stuff because you have to cooperate with it. We can't afford to throw away all the old stuff just to bring in the new because we just simply cannot afford to put in new base stations everywhere. It has to be very carefully planned out so that it can be done without breaking the bank. Digital broadcasting is another thing where digital modulation shows up. It shows up, since I listen to a lot of music, since I play music, there are standards to augment original AM radio with digital modulation for higher fidelity audio. And of course there's HD TV, but this is one that HD radio, I got more interested in it when I had to get a new car. I say had to because there was a horrific accident that somebody ran through a four-way stop and wiped out my car, could have wiped out my wife. I mean, it was terrible, actually. None of us got seriously hurt, but just like that, a block from my house, which though people always say, the accidents occur close to your house. Well, if you think statistics, now I'm thinking ahead to your homework assignments, where are you at more often than not in terms of driving your routes? What sections of road do you travel more often than any other sections of road? Those that are close to your house, right? Or maybe the route you drive to work. But so, yeah, after my car was taken away on the tow truck, it was totaled. My wife had gone to the hospital in an ambulance. I'm sitting there a block from my house, and I said, well, I guess I walk home now, because that's what I did. I mean, it was kind of sad to see the pieces of your car laying in the street that didn't get all swept up. But at any rate, when I bought the new car, it had HD radio in it, so I can listen to certain FM broadcasting stations that have the HD overlay in them. That happens to be a proprietary standard, so I don't know exactly what it does. It's a standard that you can't really see because it's not publicly available. If I wanted to learn more about it, I would have to buy a book from the company that created the standard, and that's how crazy it is. But it works really well. It increases the fidelity, HD radio. And it increases the number of channels you can have. RFID tags are also in here. There are comms applications as well. If we were to go beyond the physical layer and we look at the OSI model, then we see this stack here. We're down, in terms of what we do in this class, we're essentially always right down at the physical layer, maybe the MAC layer, medium access control layer. In terms of how our modern communications, wireless communication systems work, though, there can be games you can play with optimization by considering all of the layers of the stack. I don't do that, but some people do, and within the Communications Society of the IEEE, communications is everything. I mean, it's all those layers, and people, like I said, do things for optimizing performances and links. So it's called, I was in a proposal on this at one time, and it was cross-layer design. Okay, this is an example of a system I worked on back in 2005. It was a satellite communication system, and this just shows you the degree of fidelity I was looking at in building up the model. This was a big MATLAB model I I built for a wideband satellite communication system. And this is a link that would leave a transmitter, go through a transponder, and then go to some other receiver. In this case, this other receiver was not on the ground, it was another satellite, so it was a link that would come up and then go somewhere else. That somewhere else was part of the services that the transponder platform was providing. And it was a government application, so don't know exactly anything about what that receiver was. It was classified, but it's up there. And there are a lot of requirements in this link. And one of the things, because we were trying to use this transponder to send more bits per second per hertz of bandwidth than it was designed for originally, we were getting very close to the band edges of the transponder filters and things, that putting in an adaptive equalizer was something that the customer wanted. So this is what the adaptive equalizer looked like. It was implemented in FPGA. I was a systems modeling person, and then I worked with an FPGA developer, and this was at what used to be Real-Time Logic. It's now Kratos here in Colorado Springs. So this system worked well, and it provided considerable improvement before equalization and after equalization. This is from a paper that we published. You can see that these clusters get tighter, and if the clusters are tighter, that means the error probability is smaller. It was using a scheme known as offset QPSK, which we'll talk about. But this is what we were able to do with the equalizer, and this was based on my simulation model. There's also nonlinearities in here too, and remember last week I showed you the SALA high power amplifier model. So this had a TWT in it. Actually, there were multiple TWTs in the link, and we were required to use characteristics of those in modeling. And one of the reasons why, and this is a good thing for you guys to think about, one of the reasons why I had to build that really high fidelity model that I showed you is because it was decided that for acceptance testing of the hardware that was eventually delivered, part of the performance requirements were going to be measured in simulation, because they weren't going to be able to go do any testing at the facility here in Colorado Springs. It was going to actually have to get delivered, put in operation, and then fly some missions and just see how well it works. These things happen sometimes in electronics hardware where you don't test everything. You have some reference testing. So we had a very simple channel simulator that was used in the lab, and then everything else was inferred from the simulation stuff that I did. And then they bought off on it, and then, like any good thing, customer gets it, because it's all programmable devices. If there's things that don't work right, or things that weren't quite perfect, then firmware updates come out, and then the device gets updated in the field. We're all used to that though, right? Our cell phone gets updated regularly and things like that. I mean, we don't really know what's going on in our cell phone, but you just have to know that it's not just the operating system bug fixes. There's some firmware things that actually go into registers and change some characteristics, right?
Yep.
I know, for example, Apple's iPhone had an issue with the bars. People that don't understand that just say, I'm not getting enough bars, and they were frustrated. So I think Apple had an issue, and they changed their algorithm slightly to give a better look and feel so that people would not be so concerned. You know, we could turn the bars off. Would that be good? I don't know, but as an electrical engineer and signal processing comms person, sometimes you have to do things just because people need a warm, fuzzy feeling about the product and how it operates. So I found that to be interesting. Here's the ray tracing stuff, though. This is a PCS band model in a downtown area, and this didn't use ray tracing. This just used detailed propagation modeling, and it used a software tool or product from a company called EDX, which is makers of some expensive software that you can use for planning propagation modeling. So this just was from some of their examples, but shows the transmitter in some downtown area or metro area, and then it shows the receiver, and the color in this case tells you what the signal strength is, and this is using Waldfish Ikegami propagation model. So these buildings have certain reflectivity heights to them, and then you can get a report if you move, say if you move the receiver around, what do you see in different parts of the coverage area. So you can see what sort of coverage you're going to get. If you want to go one step further, then you can go to 2D ray tracing, and of course you can go 3D too, but this was just a feature of the software. You could do a study, and this, I believe, pretty certain is what Dr. Simiari's tool sets can do. So you can do some ray tracing modeling, and this is showing rays. In this particular case, the building models were assumed to not have any parts of the structure where we're going to consider rays passing through the building. That's certainly not impossible, right, depending upon the structure of the building. I don't know if you know how construction works, but homes are generally wood frame, so RF goes through no problem. Commercial buildings like this one, there's metal studs in the wall, and they're separated by such and such number of feet. Maybe it's 1 feet or 1.5, I'm not sure. But that forms a grid, so you can still get signals through. Like we can get FM broadcasting through because the wavelengths are short. Low frequencies don't propagate through commercial buildings very well. So our microwave, millimeter wave, we assume we do have transparency, but there's diffraction, attenuation, and dispersion due to multiple reflections that can take place inside the building. So you can see all the traces in here, though, are just external. That looks interesting, but what is really interesting is then you can get the delay spread, or what the software here called the power delay profile. The line of sight, which I guess, or maybe the shortest path, I don't think there is a direct line of sight. There's something come down here and bounce up between those two. Or maybe this is a reference. I honestly haven't played with the software for a very long time, but you can see how the distribution of the rays are for a snapshot in time. So that's the delay spread right there, that distribution in the signal strengths. Does that make sense? But now that doesn't tell you how a link is going to perform, because the modulation is going to respond differently depending upon whether it's a ultra wideband or code division multiple access, which is got a spreading code, and then D-spread, it can mitigate multipath better. But if it's narrowband modulation, then the data rate, that dispersion of 15 up to over 1,000 nanoseconds would be a microsecond. So if the bit rate was 1 megabit per second, then a bit width would be 1 microsecond, right? So we're going to have what's called intersymbol interference for sure. We'll be studying intersymbol interference, but you can see how delay spread is not good. But I say not good because last time I was talking about the telemetry link I worked on for the measurements done on ranges. The scheme I couldn't think of is called space-time coding. So that's what I worked on. Space-time coding actually uses the multipath to its advantage, and 5G tries to do that too. So they try to use the multiple paths to their advantage. Question?
Maybe this is a little naive, but couldn't you maybe use like radar techniques to kind of try to measure what your environment looks like and then change the signals you send?
Yeah, it's not naive. I don't in radar-like techniques, it's not a specific radar system, but you got it exactly right. We'll see, not with this, well, I can just cite examples that have been around since 2G where in a time division multiple access system, all the users would share the microwave band amongst other users in that cellular network. So when you get your time slot to send, you send a packet out, so such and such long, and on the original system that was developed in Europe, I'm going to draw a blank. What was that system's name? Not GMSK, that's a modulation scheme, but it's slipping my mind right now. But at any rate, that scheme had a mid-amble in it. Everybody, have you ever heard of a preamble, mid-amble? I mean, it's similar ideas. In coherent communications, we need to synchronize. So a preamble is pretty common. When the packet first arrives in a burst mode communications, we quickly can synchronize to that preamble and then get locked up and then get a starter frame delimiter and then no payloads there and bam, we're getting data across. But in an RF link where you've got multipath and things, there's other things you might do with a preamble, and the preamble might become a mid-amble so that you've got a known sequence right in the middle of that packet, and then you have known data bits that were transmitted. You can then infer the channel, learn something about the multipath, and then decide how to tune the equalizer or mitigate, do things for mitigation. So that's maybe not as sophisticated as what you were saying, but it's still learning the channel. And then every time another packet comes through, you're constantly making changes. Make sense?
Yep.
So this is in the frequency domain, and you were pointing out you're going to get some notches, and this shows it versus wavelength, but you've got some fades in there as a function of frequency, or frequency notches. This was just another example. Well, actually, what did I do? I thought I did an indoor one, but I guess I don't remember. I did one at one point that was both indoors and outdoors, but at any rate, I'm kind of done with that. There's no lack for innovation in comm systems, though. Why? I mean, just I'd say a little bit about that, but if it's military communications, it's the success of the military mission. If it's commercial communications, it's what? Making people happy, but the people that make the systems, what do they want to do? They want to make a living, so they want to do things intelligently, and they want to get a lot of customers and make an income. Okay, so I'm going to keep my eye on the clock, so we'll take a break at a reasonable time today. And I can get out of here, since I'm mentioning it. The next class comes in at 11:50, and that woman that came in was very anxious for me to get out of here. But let you know, I'm realistic. I'm like, I have until 10:40, and then I said I probably won't ever leave here before 10:40, but I'll be packing up between 10:40 and 10:45. So I don't want to be mean to her. She has a big class. She didn't think we had anybody in here, and not so. So I got to keep my eye on the clock to make sure I'm packing up and doing what I promised her to do, to be attempt to be walking out the door at 10:45. So if I appear to be very distracted when class is over with, it's because I don't want to have a conflict and I want to get out in the hallway, and I can talk to you out in the hallway. So just Um, So this introduction is maybe not needed, but if you don't do probability and random variables every day, it's not bad to have a quick review. So this first problem assignment that I've given you is probability and random variables kind of all rolled up into one assignment as a review. There might be a couple more random variable problems, I think, on a second assignment, but it's the basis for what we need in this class to learn about random processes, and then random processes, of course, is what we need to study the communications theory. I think, trying to remember between DSP and this class, I gave an example because in that class they learned about discrete time random processes, but simple example of a random process that we'll bump into really early on just to make you think is we're going to be talking about random variables on a simple probability and then random variables. One of the two fundamental random variable types that we use a lot of in modeling are, you can probably guess what two, there's two of you, maybe each one of you could guess what's a distribution that you think we're going to see over and over again.
Probably Gaussian.
Okay, Gaussian, and then what's another really popular one?
Normal,
Pardon me?
normal,
Well, normal and Gaussian are the same thing.
yeah.
And uniform.
Maybe,
Uniform, yeah, uniform. Yep, yeah, Rayleigh from fading, yeah, we'll have that too. But yeah, uniform. So
Chi-squared, right?
yeah, chi-squared when we have a some type of power law detector, and we use that for non-coherent demodulation. So yeah, we have those in when we get into that stuff. But uniform brings about the need for what random processes do. So pure unmodulated carrier arrives at me with some phase shift, say it's 10 degrees. I walk a little bit, and it's now shifted by 45 degrees or something like that. In general, when a signal arrives at us, it arrives at some epoch time, epoch as in what is the exact arrival time, and that arrival time translates into a phase shift of that carrier wave. So we want to be able to model that, and a simple model is to say it's equally likely to be between 0 and 360 degrees, or 0 and 2 pi, or minus pi to plus pi. So we use that model log. And it truly is that way, and we have to synchronize if it's coherent communications. We have to lock up the carrier. We have to phase lock to it. So in the beginning, there's the classical definition of probability, which was based on back in time, in history of the world. People just said, we're going to assign probabilities based on the number of outcomes favorable to an event and the number of possible outcomes. This definition right here, though, from the classical world, turns out to be how we apply it when we go from the theory to the practice side. We do experiments, and then we estimate probabilities using this exact idea where we count the number of favorable outcomes and divide by the number of trials that we ran. But this is rooted in the history of probability as how they saw probability, in the early generations of wanting to model things. And one of the things that comes about in this is that the basic assumption is that all outcomes are equally likely. So that was classical definition. And then we have relative frequency is a more refined version of that, and that's where you want to take the limit as the number of occurrences goes to infinity, or the number of trials go to infinity. So this is, I guess, closer to what we do with our Monte Carlo simulation. We're going to take that limit large, make it large, and we'll talk about that a lot. I'll have you study that and study the statistics of that actually. How many error events do we need to get a high confidence interval or a small confidence interval? Say we want to have a band of 95% confidence that the probability we estimate in our simulation is what we say it is. So we'll look at that. I have some neat results on that. They're available in certain books, but I added that. It's not in the textbook. The general rule of thumb, though, that I'll say is 100 error bits is pretty good. But if you've got fading and other statistical things going on, like coding theory, will change your sensitivity to burstiness and so on, you might need to go for 1,000 or more. Do you do bit error rate testing at Keysight?
I personally haven't, but like we have people that do.
Okay. We'll do a lot of that in here. Bit error probabilities, symbol error probabilities, and so on. Okay, I'll make the note in here, relative frequency is essential. Pardon me?
A lot of that challenge is making extremely high precision ADCs and DACs. I think the DSP in them is relatively simple.
But it might be, I mean, my understanding, if you want to do a really high speed A to D, you have a series of A to Ds that you fire with a phased clock so that the settling time can be dealt with.
But it definitely has to be, you have to match the clocks very well and make sure you have low jitter. And
Yeah,
a lot of the engineering in those are actually analog, not digital engineering.
right. Well, I think I told you I started my career in this space optical communications, free space, laser light, and I tell people, I guess, I don't remember what I said because I'm getting my two classes confused, but I was doing microwave and high-speed digital, and what did I mean by that is because everything was analog. Really, the gates we were using, the D flip-flops we were using were more like analog parts. And the layout and everything we had to take into account, propagation, delay times on the board is very, very critical. And the clock generator was not a digital clock oscillator. It was actually a microwave voltage controlled oscillator that had low phase noise, and then we locked that up. And then that was converted to a clock from a sinusoid, which doesn't sound like the right way to do it, but that's the way it was done in that system. It was a 1 gigabit per second free space optical system that was done around 1979. It's a long time ago. I hadn't got my doctorate then. I was just out of school with a master's degree, and I was working for the company. And we didn't do the optics. We just did all the electronic stuff. So one of my parts of my design was a low noise wideband preamplifier that was remoted from the box and would go sit right behind a photomultiplier tube, which was the optical detector. PMTs or photomultiplier tubes are probably still used today, but not like they were at that time. A more common device might be an avalanche photodiode or some other low noise, high responsivity type of photo detector. I say responsivity, that's probably the wrong term, but it's something where one photoelectron hits and there's gain built into the device, so it emits more photoelectrons. That's what this project I was going to work on for the company here, with a company here in town, was they were going to be using APDs and laser diodes. So. So as things got more sophisticated, mathematicians took this more seriously, came up with the axiomatic definition. So the axiomatic definition has got 3.5 axioms, and I'll talk about those here briefly. I was just going to say, though, where did probability play a role in early society? Does anybody have an idea? I mean, culturally, I'm not an expert on this, and I don't go to the casinos to gamble or anything, but I think throughout all history, people have gambled in some way, shape, or form. I mean, I grew up in a house, and I'll look at both of you. both of you have siblings?
Yep.
Did you ever have rules in the house where it's your turn, or did you have the deal where we're going to, my father's famous thing was drawing straws, or it could be matches or something where you have little sticks, and he would hold them in his hand, and you would see the tops of them sticking up. One of them was longer than the others. So it'd be like, you have to do this, we're gonna draw straws for it. Called it drawing straws, but it could be a little piece of wood. You pull it out, you don't know which one's gonna be the longest, everybody pulls theirs, and then they have to compare them. Whoever has the long one has to do it. True? Do you ever do that? There's probability involved there, right? So I never did that with my sons, though. I have twin sons, and it was easy with two. It was like, I think, an alternation. But if you have more than two, and I grew up in a household of four, so we had to do stuff like that. So axiomatic definition, we come down with a sample space, and the sample space encompasses all the possible outcomes in the underlying random experiment, and there's a certain types of experiments that have a countable number of elementary outcomes, or those that have an uncountable number. So the example here is kind of depicted as being a countable number, but you take then those elementary outcomes and form from them events. It might be, if it's rolling a die, it's really simple to talk about the idea of the event space from the sample space. A sample space does not yield necessarily an event. A single elementary outcome is not defined an event in the axiomatic approach, because that event, that single elementary outcome, may occur with zero probability. I mean, what I'm thinking of is if you put numbers on a number line between 0 and 1, they occupy all the real numbers. How many real numbers sit on the line between 0 and 1?
Infinite number.
Yeah, uncountable infinity. So can I assign a non-zero probability to each and every one of those?
Right.
No way, you can't do it. So we have to think about those scenarios where we have to do things differently. But for the die experiment, it's pretty easy. If we wanted to have the event of rolling an even number or an odd number, then we know it just depends upon, whether the face is an even number or an odd number, and then we can come up with the die. The probability of an even number can be assigned 1/2, even number 1/2. So this is what I was just talking about. Subset is a collection of elementary outcomes. They all are contained by the sample space S, and then we can set up events that are collections of the elementary outcomes, like I said, even or odd face count. Subsets of S, which make up what's known as a sigma field in abstract algebra from mathematics, are formally definable as events. The sample space itself is the certain event, and the empty set is called the impossible event. The business of sigma fields is kind of beyond me. If you were to take advanced calculus or real analysis and get into measure theory, that's where you get into properties of the sigma field idea. I just bring it up because I got introduced to those things and have attended engineering conferences where the presenters are mathematicians, and sometimes you'll do that in your life, and they'll blow you away with the preciseness, and you'll say, why are they doing this? Because they're mathematicians and they want to be incredibly detailed. So axioms of probability then are this. probability of an event is greater than or equal to 0. Probability of a certain event is 1. And if we have two events that are mutually exclusive, in other words, we intersect them, the underlying elements in each of those events, none are in common, so we have an empty set when we intersect those two sets. Then we have this third axiom, which says the probability of the union is the sum of the probabilities. And this is a foundation that you build probability on. And the extension to that is taking a number n of mutually exclusive events and intersecting them, and then you get the sum of the probabilities. And this is the beginning of the idea of total probability, but this is the 3.5 axioms idea. And then a bunch of simple things follow from this. We have complements, which is used heavily in the very first homework problem. We have joint probabilities where we're going to where we're not going to union, we're going to intersect. So when we intersect two events, we get this notation, and that is called a joint probability. And a joint probability has to be made by assignment. You have to know that you have to know something about how it came into being by definition. You can't just say so. But where we use this frequently is we'll say event A and event B are independent of each other. So then we'll use the idea that independence just means we have the product, and that actually comes out, I think, way over here is where I talk about independence. Maybe not until way out here. You can define independence by other means too. You can use conditional probability, but first couple of homework problems revolve all around probability stuff, and I don't know. I'm about ready to take the break, so I'm going to take the break here momentarily. But if you're thinking back when you had probability and random variables, first off, what types of problems did you like, dislike? I'm just kind of jogging your brain. I'll give you my examples. I didn't like pure probability problems that are set up as a story problem, where you have to read and then take the information they gave you, make a few assumptions about things, and then just put it all together. It's kind of like when you first have story problems in mathematics, you have to read it over and over again. Does it say that or does it say that? And
Yeah, we had story problems where we had to figure out what kind of distribution the problem was referencing and then determine the probabilities.
yeah, and wrapping all this stuff up. Random variable problems I tend to like better because random variables just seem to be more you can grab onto, and engineers, I think, like those problems better. But in communications theory and digital comm, we have to deal with both. So random variables, though, mostly. Let's take a break. It's about 9:27, so let's come back at about 9:40 or 9:37 or something like that, about 10 minutes.
Okay.
So I'm going to stop or pause my recording. So things with probability that you're familiar with that I just had reviewed here in the notes. We have the axioms, but then we have a number of useful relationships. Complement. What is joint probability? It has to be given to us. We cannot infer it, so maybe I should just write a note in here. Just say need more info. Unless somebody tells you but doesn't say anything else, you can't create a joint probability without having somebody give you that information. But if they say independent, like in homework problem number 1, you are going to be able to do things with this joint probability because by assumption, things are independent. Does that make sense? And that's the thing, just before break, what I was saying, what type of problems do you like or don't like? It's those story problems where they give you words and there's key phrases in those problems where you have to infer mathematical properties from those words. Agreed? I mean, you struggle with that in the beginning. It's like, how can I say that? The words and how you read the words. And if you're reading English and you're not an expert on English, I guess maybe you have to translate it somehow or another, but the problems are written with those words being used. Generalization now, a simple axiom generalization, which occasionally would be used, really not that often in this class, but actually it does come up because we have something called the union bound, which we'll be using eventually in digital comm. Says that the probability of the union of two events is going to be the sum of their probabilities minus the probability of their intersection. And that, you can always utilize the Venn diagram to say that, okay, obviously you've got something like this going on. If my pen will draw on there. So that one sticks in your head, right? You probably learned this one and never forgot it. So we use this one a lot in modeling only because the union bound, then the union bound gets added to this to say, right? It's overbounding some of those probabilities. Conditional probability, very important in breaking problems down from their starting point to get somewhere, get some traction going. So A given B is just the joint probability of A and B over the probability of B. Then B given A is the opposite of that. The way I think about conditional probability, again with a Venn diagram, just to refresh your memory. So when you think about the Venn diagram, what's really going on is if you're going to say, let's just go with the second one. Let's go with this definition here. So what conditional probability is doing, it's reducing the sample space down by the conditioning event. So we're conditioning upon A in this second scenario, probability B given A. So now you're going to find that the probability of B given A is going to involve the intersection of A and B divided by the probability of A. So if I was to draw the cross-hatching in here, that's the probability of A, and then the intersection is where they overlap in that area, and then it's just the ratio of those probabilities. So you're normalizing it to a different space, the conditioning event space. And then you combine them together, you get Bayes' rule, which we use frequently too, the random variable version at times. I'm going to let you look at this one because I'd rather go look at the homework problem. I'll just say that this is a heads and tails coin flipping example. But this is the story type of problem. So what I want to do is go a little bit further, then I'm going to look at homework problem number 1 and probably number 2. I brought my solutions in, so. Maybe it's not 2. 2 is pretty easy. Well, let's see. Probably don't need to look at it right now exactly. Oh, yeah. it is 2, I guess. So then we have the theorem of total probability, and that's just built off of the definition of conditional probability. I would call it, if I was to call it by another name, I would say divide and conquer, because that's what you do with total probability, right? You have a means of getting at some probability, say probability of B, but you don't know, you want to break it down into its constituent parts. So you find how B projects on a subset A and or a subset A1, A2, A3. So you're breaking it down into pieces like that. You're going to find the probability of A by finding out the probability of B given the probability of B given A1, weighted by the probability of A1 itself, and then you find another partition. So again, the Venn diagram for this one, if this thing will work, this is a simplified, abstracted view of it, but this would be A1, A2, A sub n, so, and the red box is always a sample space. So if you're finding the probability of B, you're going to find the component probabilities of B given A1, A2, and so on, and then weight them by their corresponding probabilities of A1, A2, and A sub n. Because this thing has a requirement that the partitioning of the sample space is done with mutually exclusive partitioning. If you don't have that, this idea doesn't work. Proof of it right there. So an example of some of this, and this shows up in information theory where you'd have this fundamental, what's called the binary symmetric channel model. And this is how Shannon looked at communications. He didn't look at the physical layer initially, he just said abstractly, I have an information source on the left, and I'm going to be sending information to the sink on the right. And I have this way of viewing my channel very abstractly, saying I try to send a 0 from the source, so 0s is 0 from the source, and I'm going to look for something coming in at the sink or at the receive side, and the process of sending it over the link is possibly going to morph it or make an error. So this is 0 received given a 0 sent, and then this is the channel flips it, and likewise the same thing happens when you try to send a 1. And binary symmetric channel, this is a general channel model. It's not defining the probabilities, but the symmetric channel is where the upper and lower paths that cross over are identical probabilities, and then the cross paths are identical, right? I'm sure you've seen this before, so it might be P and Q or something like that. Yeah. In my notation, this will go there. This pen is having a wireless problem. It has to be reset. P. So P plus Q equals 1. And that's probably not stated anywhere, but it's obvious, right? If you're going to transmit, it's going to have to go somewhere. It either has to go a cross path or a direct path, so the probability has to add up to 1, because that's the sample space then. The sample space in this case, if you're just homing in on that transition point up at the top left there, it's going to turn out to be one of 2 events that are going to take place. There's not an option in this case if there's a null event where nothing happens. So you can define these events like I drew on the picture, and then we have the symmetric channel case, and suppose that P is equal to 0.9. Then we could go off and find we could find a conditional probability, probably that we receive a 1 given that a 1 was sent, and find the probability that a 1 is received. So those are just two different side calculations that we could do. And we'd refer back to this picture and then do those calculations. So first of all, to get the probability a 1 is sent, given that a 1 is received, we would go with Bayes' rule, and we could take 1 received given a 1 is sent, which comes right off of the channel model itself, and then times the probability that 1 is sent, and then divided by the probability that 1 is received. To get the 1 is received, though, that requires the use of total probability, so that has to be done off to the side. So this is that. And the green checks there just mean those are given to us from the problem statement, right? In this particular case. So then you can just go ahead and plug the numbers into it. That's the other thing about these discrete probability problems. You end up writing the math down fairly quickly, but then you start scratching your head like, where am I going to get that from? Can I get that? Can I infer that from the given information? In this case, it's the probability that a 1 is received. You have to say, well, it can arrive at me as a 0 that was sent, got flipped to a 1, or it can be a 1 that was sent that stayed as a 1, right? And that's where the total probability idea comes in, as a way of flipping the problem around and being able to solve for that. This is extremely simplistic, but that's the nature of probability theory. In the end, you spend a lot of time with your brain exercising, convincing yourself this is it, and then when you actually carry out the calculation, it's pretty easy. And here's the Bayes' theorem result here. So, definition of independence is just saying events are statistically independent if the joint probability A and B, and always remember, like I said earlier, those are alternate ways of writing the joint event, or actually, those are three different ways that we see it in practice. The A times B is what we see in the typeset version, and then mathematically we might use the intersect symbol, because thinking that A and B are events, or a lot of times we use the comma in between joint event A and B. So you just have to see that notation and then say that's what it is. And if you're confused, or if you're getting caught off guard, just pick another version of the notation if that clears up your thinking process. I'm not a logic circuits person. I didn't take logic circuits actually at my school. I'm old enough that it wasn't a requirement for me. So I don't get confused maybe as readily as you might, because you maybe had logic circuits and think differently. I just think in terms of the mathematical definition of probability. But statistical independence means that the joint event is the product, and this extends up to random variables and random processes. And it's a very powerful, it's probably the most powerful probabilistic related property that we utilize, independence. Love it. It simplifies things tremendously, but it's not always a valid assumption. And this is true in life. Is your decision independent? I guess I'll say of a married couple, since they do a lot of their things together, you might say, if my wife gets COVID, chances are I'm going to get COVID. Just as an example, that sort of a thing. But if my wife is in a car accident, I'm not trying to be morbid, I'm just picking a simple example. Am I going to be in a car accident? Not necessarily by any means. I mean, we go out and do different things throughout the day. So, then you can say in a practical probability sense is which of those two are more likely to be independent. We can't prove them unless we actually do a bunch of experiments, but correlation experiments. I didn't think this all the way through, so my example is not rock solid on does it show one is independent, could be independent. It'd be more likely though that us being in a car accident be independent, but still I know it's not true. Why do I know it's not true?
Sometimes you drive together.
Yeah, we drive together. We absolutely drive together. If you never drove with your spouse, then that'd be the only hopeful way of saying they're independent. But otherwise, there's always that chance, right? Agreed? Okay. So, and then the idea of conditional probability leading to independence makes a lot of sense, because if you say A and B are independent, then A given B, the statistical or mathematical property, you can't draw this in the Venn diagram, you'd say that B occurring has no bearing on A statistically, so that statement is true. We'll do Bernoulli trials in a second, but before we do that, I want to just jump over to talk about the first homework problem. So I attempted to draw it out here. This is kind of a classical problem, and I think it's a fun kind of a problem. It just gets you thinking again about probability. So this is, you can draw this type of problem in different ways, but this is the way Dr. Zemer drew it. He said you've got two nodes in a network, A and B, and you want to have messages sent from A to B, and you've got paths that you can take to get the message from A to B. You can go diagonally from A to B in path 2, or you can go the lower path, top to bottom and then across, that's 1 and 4, or you can go 3 and 5. So in the statement of the problem, first off, given that all links have a probability of being up or being down, broken, not functioning, with probability P, and then the probability that the links are up is Q. Now what the problem does not state, but you have to infer, is what? What seems like you're missing here? I'm just going to read, I have written on my solutions exactly the words of the book. The figure below represents a communication network where the nodes are receiver/repeater boxes, and the edges or links represent communications channels which, if connected, convey the message perfectly. Then the P is the probability the link will be broken, and the Q is the probability the link will be whole.
So the assumption is that all 5 links have independent probabilities?
Yeah, so failing. It's right in that area where he's telling you the probabilities of the links, where it'd be nice if there would have been some more words there, right? But because the words are not there, and you don't want to look like you're dense and can't think, you can either ask me, and I will say, yes, of course, but I would have added in another sentence or another comma, something like, and the links fail independently. But that's part of the assumption. So, then just looking at part A, and there's 4 parts to this problem. Part A says find the probability of at least, I missed the letter in here. At least one link is up. So I underline at least, because that's a very key statement when you work this kind of a problem. At least, no greater than, all these other, little things that get added into phrases. So at least means what? One or more links is up. So you're going to solve for the case where not just one link, exactly one link is up. I mean, that's the other part of the wording. Instead of saying at least, you could say exactly, but that's not there. So at least is interpreted as 1, 2, 3, and so on. Got that?
Mm-hmm.
So he talks about in the book using trees, kind of a lower level of assessing it. My preference on working these problems is to try to gain as much traction as you can as quickly as possible. And what I recommend that you do is you switch to a complement mode of thinking in this type of problem. So you always have to kind of be on the lookout when you work problems kind of like this is, am I going to solve the probability that they want, or am I going to solve for the complement of the probability? Because what's the complement of at least in this case?
All of them are down.
All of them are down.
You're right, that seems to be the easier one to solve.
Yeah, almost always that works out that way. And that's just a mindset thing. And you can go count them. But if you go for the complement in this case, that's much easier. Can we agree? Would you agree with that? Or I think when you're working any problem, though, if you're not sure that's making sense, you can think it through more. There's some problems I have in the statistical communications theory class, which does a more detailed probability review, where these are mind bender problems where I searched around to find some really hard problems, and then you can maybe have to write out some math to prove yourself that it's correct. But in this case, you're going to go after that none of them are up. And when you're talking about none of them are up, then you can use the definition of joint probabilities. You're going to be looking at independence and taking that one step beyond what we've already done. So if you have that'll be one path, that'll be the second path, that'll be the third path. So if you get the probability of success and going down that lower path, then then you'll be using complements at each step of the way, and finally you break it down. So you get the probability of going from down that lower path, and then the probability of not going down that lower path will be the complement of that, 1 minus that probability. And then you do that for the diagonal path and then the upper path. And then eventually you're going to be wanting to get the probability of the joint event, which is failure on, the joint event in this case, you get the probability of failure on the lower path, diagonal path, and upper path. And that will break down into the product of the probabilities. And then the complement of that, so you're going to be just flipping this, using this complement idea and independence sort of in a couple different layers. Make sense to you?
Yeah, that makes sense.
And everything else follows in the same manner.
I haven't thought like this in a while, but I'll pick it up again.
Yeah, you will. That's why I did this, because I just wanted to have this be a way to go. And we're going to have other things when I get in, and you are using random processes. We'll be doing things with waveforms, and we'll be thinking about, signals and time alignments, and it'll still underlie it will be these types of ideas, though. This is in probability. When they get into waveforms and random processes, we'll still have things of this sort, where we're looking at, say, intersymbol interference and combinations of things and complements and that sort of stuff. So that's why this review is kind of nice. So the next part of the review is Bernoulli trials, which is repeated experiments. So Bernoulli trial is doing some experiment n times. Each trial has a binary output, P or Q, and then we combine the experiment. So formally it's called a Cartesian product, and you get an n-tuple or n-tuple of outcomes, and these chi sub i's are used as the indicating those trials. And now, if you go with the Cartesian product space and you put together all those different types of experiments that could possibly exist, your mind is blown away by the reality of that. But the Bernoulli trials case is much simpler. It's just saying same type of experiment over and over again, and we're just interested in, you know, the on or the off type scenario. So then we can take Bernoulli trials down to the next level of assumption, is that the sub-experiments are independent, and then use the definition of independence to handle the joint event. Not all problems work this way, but this is a very common scenario. So what we're looking at here fundamentally is we're looking at occurrences of events where we're going to have the event A occurring successfully k times in a particular order, and that is a counting problem. And if we go back to our idea of independence, then what we had in that statement right up here, we might think of this as being a vector, and those are the elements of the vector. So when we're counting things off, we're going to have a specific order of P's and Q's, and then because of the independence, we're going to have the products. We're going to have P to the K and Q to the N minus K as the probability associated with a particular ordering of, say, events. I like to think of it probably easily as just calling it bits, you know, zeros and ones. Either it's on or it's off. So if we want to extend this then to say we don't care about a specific order, but we care instead about the total accumulated amount, then we can just use the combinations counting formula and say that the number of sequences where A occurs k times in any order is just the binomial coefficient n choose k, which is the n factorial over k factorial times quantity n minus k factorial. So finally we get the binomial probability from this idea of Bernoulli trials. A occurs k times in any order. So we have the underlying probability of a specific order is sitting right here. And then the multiplication factor. To add up the number of combined experiments where we get a specific order. And that's really just using independence again, all those, or we're using axiom 3.5, where we're saying the number of mutually exclusive events, we can then take the probability of the union and add the probability up because the events are mutually exclusive, right? This I guess is what makes it hard to get probability going in your head, because you got to weave all these things together and know how to weave properly. True or not true? I think it is true, because once you've done it enough times, you just say, look at it, but think back to when you first started doing it, and I've taught undergraduate probability, not for a long time. Wow, it's really hard, because the students that get it are bored to death, and the students that can't get it are they're just lost. I mean, it takes a while for it to start clicking. I think this is one of the hardest subjects to teach, actually, for beginners. Okay, a little example in here, just to see how you can take this to a limit. In digital comm would be bit patterns, as I call them. So bit pattern would be maybe in a preamble or some other embedded code word in a series of bits. Or in a waveform, it might be a waveform where you've got pulses that represent zeros and ones, and you're looking for patterns. So here the event is, here what we're looking at is event of 2 ones in k bits. So, and then we're going to stop looking for a pattern. So it might be we're trying to sync up or wait for that first occurrence of that scenario. So the way I drew it out here is we stop when we see the second one, but the first one can occur in any one of those slots up front. So what sort of a distribution do we get out of that? So first off, assuming independence between the bits, we can write P of k given 2 ones is going to be this equation right here. So how do I get that? Yeah, I'll just walk you through it, and you might see it already. There's 2 ones in there. So this is just the binomial expansion. This is 2 ones in any order. One happens to be fixed at the end of the interval. So that's the p squared, and then there's k minus 2 zeros, so and then the binomial coefficient value comes about as k minus 1, and I'm not doing any factorial, I just simply look at the underbrace there and say that that single 1 before we get to the end can occur in any one of those k minus 1 slots. So that's how I count the number that I have there. So that's how that probability comes into being. Now, you can go ahead and form a sum of that. The probability that 2 or more bits must be observed until 2 ones occurs should be 1. And so the 2 or more means that if I take and look at how I have a distribution of probabilities, that if I take the limit, that probability is going to be 1. And that intuitively that makes sense, right? If you in a rare instance, you're going to have to let k go all the way out to infinity before you finally get that second 1. And then you say, I'm done. I've been waiting and waiting and waiting. So if you then take all of these sequences of zeros and ones and find out what the sum of those that probability is, it should equal 1 because it should form a certain event. So I did that in here. I said I just as an exercise, but as an exercise in the types of things you may bump into. What's the probability that k, you stop at when you get 2 ones, is greater than or equal to 2? So this is, answering the question that I have here, 2 or more bits must be observed till you see 2 ones. So write out that sum, jump into it, break the sum apart. Here I break it apart. So I have 2 different types of sums in here. If you go look at a math handbook, there's 2 different types of series here. One is a geometric series. What's the other one? Which is the geometric series, if you remember back to math?
The first one?
Okay, the first one is the geometric series. Second one is called, remember, I'm just curious, it's something you learned in calculus probably. Arithmetic geometric series is what it's called. So we have an arithmetic geometric series. I have a math handbook in my office. I could type and do symbolic sum routine like in SymPy or Mathematica, but plug all those numbers in and I get 1. It seems silly, but it's kind of cool. I think it's very cool actually to be able to say I contrived a problem. It's kind of a silly problem, but still it should, intuitively, it should add up to 1, and sure enough it does. If this wasn't true, what would you say? I violated the axioms of probability, saying that the sum of all the mutually exclusive events has to cover the space of possibilities, and it cannot be less than 1, it cannot be greater than 1, it has to be exactly 1. So I find that really confidence building. Okay, I was going to look at the second problem. I'm looking at the clock. The clock is ticking. The next problems involve random variables, except, yeah, I guess I won't talk about number 2. I'm going to go until we get to within 5 minutes. I'm going to see if anybody's got questions on any homework or something. So the next thing is random variables. Random variables just takes us one step up from probability theory and says now we're going to have a rule that assigns a numerical value to an outcome of a chance or random experiment. So we're going to map the elementary outcomes in our sample space onto the real line. And this is where the idea of the capital X is a function of one of the chi sub i's in the sample space. So most textbooks use a capital to denote the random variable, and then they'll use the lowercase down here to denote the value the random variable can take on. I taught out of a book one time, well, many years, Papoulas, a guy from New York City, one of the core universities in New York, maybe it's Columbia or I don't know where he's from. I'm sure you haven't heard of Papoulas. He's been deceased for quite a while. He used boldface for the random variable. And I still will be using boldface every now and then, so you might see that leak in rather than capital. But the Ziemer and Treiner book uses capital for random variables. So it's just a mapping. And yeah, here's my note about Papoulas and the boldface. So we can characterize a random variable by its cumulative distribution function, which is finding the probability of this event that the random variable takes on values less than or equal to little x, is called the cumulative distribution function. It's a mapping, and this relationship over to here is just telling you what it underlies in the sample space is it's all the elementary outcomes such that x of that elementary outcome is less than or equal to little x. But end to end, we don't really care about that anymore. Once we establish what a random variable is, you just look at both ends of that and you just say it's where the random variable is taking that value is less than or equal to x. So it's 0 at x equals minus infinity, and it goes to 1, or it limits as x takes in all the values on the real line. All the mapping has to have taken place, so it's equal to 1. It has a right continuous property, so that as you approach from the positive side of the x value, you will have continuity maintained, and it's a non-decreasing function. So as you increase x, it's monotonically increasing. And when you have discrete probability, the CDF has jumps in it. So wherever, this is a picture of a CDF that has both continuous and discrete probability assignments in it, but if you have a jump where you can see it's discontinuous at that point, but it is right continuous, as you approach from the right-hand side, it's continuous. That's just an indication that there's a lump of probability there, and that occurs in our world of electrical engineering when you have some sort of a nonlinear thing going on in a waveform, a processing element or something like that. Okay, probability density is a more common characterization for random variables. That's just taking the derivative of the CDF, and then you get, flipping that around, you get the integral from minus infinity up to little x of the PDF is the CDF. Both provide a complete description of a random variable. I really like favorite existence theorem or property for random variables is it's any function that is non-negative and integrates to 1 is a valid PDF. So those first two properties there actually form what's called the existence theorem for a random variable. So you can create your own PDF at will as long as you can make it satisfy those first two properties. So maybe favorite was not the right thing. Favorite was supposed to be actually the this. I say favorite because if that's true, then you're good to go. You have something you can use for modeling. Just showing you what happens when you have a PDF that's got continuous and discrete. You have a delta function sitting in there because we're going to assume operationally when you take the derivative of a discrete jump, we're going to say in an engineering math sense it's going to impart a delta function. And then when we integrate that assuming that we have a limit that covers that infinitesimal width, and we'll integrate that lump of probability that sits where that delta function is. So important probabilities for us initially are uniform and Gaussian or normal. We mentioned those earlier. One of the homework problems involves exploring the area under the tail of a Gaussian or normal PDF. Our book likes to call that the Q function when normalized in this fashion. So we'll use the Q function a lot. In Python, it's called the survival function. That's the name of it if you use the statistics package in SciPy. MATLAB and Python both have.
So actually, that leads to a question I have on the homework.
Okay.
How much of the homework do you expect to be done by hand versus with help of Python or some computer?
Here's the basic idea of what I do. Good question, and maybe I'll have to stop after this because I'm going to run out of time. Let me just finish this, and then I'll answer that question. So other contexts will use error function and complementary error function, and they're related. So it doesn't really matter what we have. Q function, ERFC are kind of synonymous with one another. And then the ERF is the complement of the ERFC. So and that's all this discussion in here. The homework problem you have is involved with one approximation to the Q function. a rather crude approximation to the Q function, but one that's very handy at one time when you're using a calculator only. Whereas this is a little bit a very tight approximation to the Q function. But when we have tools like MATLAB and Python and so on, we just have it available to us. We can just use it directly. So that's why that homework problem, I want you to compare, just for the fun of it, compare this to the simple approximation the book talks about, and that approximation is, it's over here. If I look in Slack, I did put it in here. Oh, yeah, it is in here. This is equation 6.202. This is a simpler large argument approximation for the Q function. So in terms of mathematics, handwriting, and using the computer, I'm fine with you doing it all in a Jupyter notebook or something like that, where you can just convert it to a PDF that you can ship me. But if you have to write some math out, which you do have to do for some of these problems, like the first problem, for sure, you need to write out that stuff all the way through. You might decide to do some plots, I don't know. I'm just looking at problem 3. Problem 3 is a certain continuous random variable has this piecewise definition. It has 2 arguments to it. It has A and B. So it says find the arguments, proper values for A and B to make it a CDF that gives a certain value, and to make it a valid CDF. So you have to treat that as if, okay, I need to define A and B to make things happen, and you're going to have to do that by writing some things out on paper, but you can write that into the notebook too. I mean, my solution, you can just see I just wrote my answers out right here. I just wrote up in math, and I did it on the computer. But then in some of the problems I draw some pictures and do some calculations in Python, or some of these solutions I have in here were done in Mathematica, so I was using the symbolic solver. I gave you examples of how to use SymPy in that sample notebook that I put up for problem set number 1. Remember that from last week?
Yep.
So you can use SymPy. Do you use SymPy? Or have you tried using it?
I've never used it just because most of what I do is numerical.
Okay.
But I'll learn it.
You don't have to learn. I'm just saying it might be something that's curious to you sometime or another. But
Sure.
but NumPy or SciPy.stats is pretty handy.
Yeah, but I use that a lot.
Yeah. But you can also use ERFC and ERF that are built into NumPy too. I just kind of become familiar with the tools. 10:36, so got about 4 minutes left.
I said we should have cleaned our homework tonight.
No, you can. Actually, the best way I'd like to get the homework delivered to me would be for you to go right into Slack and just,
Private message you on Slack.
yeah, just direct message me on Slack with an electronic version. Is that good?
Yeah.
If we get trained up on that and COVID gets really bad, this is what I'll be having you do. So if we just start doing that from the beginning, it's probably a better habit to get into.
Okay.
And I'll push stuff back to you that way too. And I'm going to be pushing out the hints. So I'm going to shut the video off, and we're going to establish what our password is. So goodbye to anybody watching the video, and the password will get mailed out or Slack messaged out. So I'm going to stop this.